Howdy and welcome back. So we just introduced sign magnitude notation where we said effectively if we had a 4-bit integral number, we would go ahead and reserve one of those bits exclusively to determine whether or not the number that was encoded was positive or negative. This cut the effective range of values that we could store down by n power of 2 because we removed one of those position values that could contribute to the to a binary number, and instead it's simply there for to communicate the sign. And we said that using 4 bits. Now in this case we could effectively represent the values -727. However, we did notice some problems with it. First is that, basic binary arithmetic that we introduced in a previous video didn't work out so well. For instance, adding a positive number 3 along with its negative counterpart. So 3 again, we observed a value of -6, which is a result that mathematicians would consider incredibly wrong. So this encoding schemes, it's nice, it's real nice idea. Okay, it's just on or off, but maybe it's not as nice as we had on our first impression. We've had to reduce the kind of the range of values that we could store because we had to reserve 1 bit for that signage. Then two, what we're now figuring out is, well, basic arithmetic isn't quite working out using the sign magnitude notation. In addition to this, we saw that some numbers are encoded twice. For instance, 0. We now have both positive and negative zeros. Take that as you will. But we'd probably prefer to have a representation where we only had to consider one value as 0, opposed to the 2 that sign magnitude notation provides us with. So here's a second idea, and it kind of goes off of this idea of additive inverse. Based on the limitations of sign magnitude notation, what I think we really would like to have for integral values is an encoding scheme such that for any x plus its negative counterpart, we want that to add to 0. And in this case, or that is, we would like to store negative numbers as the additive inverse of their positive counterparts. That is, how can we encode a number, a negative number, is answered by figuring out what value we would like to add to its positive counterpart to get 0. So with 3, what would we need to add to it to get to 0? Well, this is going to prove problematic if we're trying to do this with only 4 bytes of representation. Because to add to 0, what we're, if you add 9 plus 1, just assume we have one kind of one digit that we can store the result in is, well, there's a 1 here that kind of needs to get carried. So the additive inverse is almost always going to require 1 more bit than you actually have. So we can't really add to 0, 0, 0. So there's no value that we can use kind of in the place of the question marks that is going to make this work. However, recall that our values can be represented by a limited number of bytes or bits depending on the kind of value. Anything but beyond that is lost. Therefore, we do not need the total to be 0. So we don't have to worry about just getting all zeros, the result of this computation, into 4 bytes. Like all we need to be concerned about is that we need to get 4 zeros, and anything that does not fit within the finite number of bytes that we have is going to get disregarded. So with this in mind, that anything beyond the 4 bits of representation is lost during an arithmetic operation, we do not need the total to be 0, but we need 4 digits of 0. In this case, what we're really looking for is what binary value can we add to 3 to get 4 bits of 0. Because if we can only store, so if we're using an integer representation that only has 4 bits, right? And anything beyond that is lost. All we have to do is ensure that 4 bits get into those slots, and this 1 will inevitably, it won't be stored anywhere. So what can we add to do this? Well, this problem is solvable because the most significant bit, that 1, is going to get, it's not going to be recorded anywhere. It will be lost and it will not be stored in the result of this computation because there's not enough bits to store it. So we would therefore encode -3 as 1101 because when we take these two 4-bit numbers, 4-bit integral numbers where we're using this additive inverse encoding scheme, we have 4 bits added to 4 bits and the result stored, because our data type for this example is only 4 bits, adds to 0, because again, this value here, we don't have a place for it, so it gets lost. The way of encoding sine numbers, this way of encoding sine numbers, that is known as 2's complement. To compute the 2's complement for any positive integral binary number, all you have to do is flip all the bits and add 1. So notice here, if we wanted the 2's complement of 3, so +3, we'd like to know what, how would we encode -3 such that this added to its additive inverse would add to 0? Well, first we're going to simply flip all of the values. So that's 0, 0, 1, 1. And then what we're going to go ahead and do is, in the second step here, add 1 to it. And our additive inverse of 3 in base 2 is going to be here. The negative value here is going to be 1101, which is what we found up there. Note the most significant bit here is not exactly a sine bit, though it can be used to determine whether the integral binary value encoded is positive or negative. What do we mean by that? Okay, let me get a piece of paper because this is, once you recognize what's going on, it's easy to understand. The first time I saw this, it was not trivial to me, and it took me a while to kind of figure out how this works out and how we could say, in this case, use 4 bits to represent both positive and negative numbers. Because how do you, where do the positive numbers go? Where do the negative numbers go? I only have 4 bits, so that means this, the range has to be partitioned in some way to accommodate those negative numbers, which means I don't really have 0 through, what was it, 15. I now have some negative number to some positive number, some range. And how do we get that to work out in a nice way? Well, give me 1 second and we'll work through it together. Okay, so here's some paper. So we were saying, we're just sticking to our example, we had 4 bits. And let's consider this unsigned first. What is the range of values that we can store? So let's say we have all zeros. So that's going to be 0. And then we'll go ahead and do this for all 1s to find the upper range on this, 1, 1, 1, 1. So this is going to be 2 to the 0 times 1 plus 2 to the 1 times 1 plus 2 to the 2 times 1 plus 2 to the 3 times 1. So the upper end of the range here is going to be 1 plus 2 plus 4 plus 8, and that's going to be, or 15. So if we're only storing positive numbers, the range of values that we can store here is going to be 0 to 15. Again, assuming all positive numbers. Let me draw out a number line here quick. Okay, so here's the range of values that we can represent, 0 through 15. Again, we're just considering that this is unsigned and we can only store positive values. What happens if I do the following? So 4 bits. Say we have 15. Let's say to it, we'd like to add 1. And that result Well, we only have 4 bits, so it's going to be stored in 4. So 1 plus 1 is 0. Carry the 1. 1 and 1 and 0. It's going to be 0. Carry the 1. 1 and 1 and 0 is going to be 0. Carry the 1. 1 and 1 and 0 is going to be 0. Carry the 1. And remember, this gets thrown away because there's no place for it. So we almost kind of can begin seeing this as actually allowing us to store these values 0 through 15. And when you get to a point, you kind of loop back around. Okay. So now, with this in mind, let me draw this out a bit differently and see if you can see where we're going with this. Okay, this is kind of an interesting diagram, but I'm trying to show you how this will work out with 2's complement. So if we consider the whole range here, and I've just kind of taken the number line and I've rotated it. So we can think about, there's a dot here. There's one here, 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 here. And now we're kind of looking at this in 2 dimensions. And what I'm trying to illustrate here, we'll see if I get through or not, is, okay, at the top end, we have 0, right? 0. And then if we look at this kind of side here, this is 1 through 7. And because we're using a positional system, where does that fall in our bits? So 7 is encoded as 0, 1, 1, 1. That means this side of kind of this, I don't know, connected and reoriented number line into the 2 dimensions contains 0 through 7. If we now look at this side of it, notice that we contain 8 through 1, 5. So 8 is going to be 1, 0, 0, 0. That's 8. And 1, 5 is going to be 1, 1, 1, 1. Now notice when you get to 15 and add 1 to it, you arrive back at 0. So if we kind of think about this, and if we just continually add 1 starting at 0, we'll visit each pop here. Adding 1 to 0 gets us to 1, 2, 3, 4, 5, 6, 7, 8. I wish I would have done this just to 8, 9, 10, 11, 12, 13, 14, 15, and then back to 0. So here's the idea with 2's complement. Let's reserve this side of this number line for positive values. So in this case, we'll be able to represent 0 through 7. Let's represent the other side, or let the other side represent the negative values. In this case, -8 through -1. And you go, well, where's -1 coming from? Well, remember, we want 1 and its additives inverse, so whatever's in blue, to add together. So the orange, maybe we should have made 0 a special color here just to add some green to it, because that's what we're trying to get to. We want a blue and an orange to add together such that we get to 0, because we need to encode both positive and negative numbers using 4 bits. So we have to partition the space in some way. So we'll just say everything up in the first 3 bits is going to be positive, and then we'll use the other side of the representation, 8 through 15, to encode the additive inverses of those values in orange. So working, and hopefully this is where it will begin to click. That means that -15 would store -1. Notice that 1 and 15 are kind of equidistant from 0 when we've rearranged this. So -1, so positive 15 in an unsigned 4-bit representation. And the signed representation, 15 is actually going to go to -1, 14, -2, 13, -3, 12, -4, 11, -5, 10, smaller and smaller, -6, 9, -7. And then the cool thing about this is that we do not have positive and -0. Instead, we get one extra digit in the negative kind of side of things. So that's going to be -8. So our range using this, using 2's complement or this additive inverse scheme of 4 bits of 4 bits is going to be 7. Let's start at the lower end. -8 through 7 is the range of values. So it's important to point out here that 15 serves as the additive inverse for 1. Notice here they're equidistant from 0. So adding 1 to 15 gives us 0. So we'll go ahead and encode -1 as 15. Likewise, 2 and 4 are additive inverses. Adding them together will have us arrive at 0, which means that 14 is the proper candidate to encode -2. This holds true for 13 and 3. So -3 will be encoded as 13. Same for 12 and 4. And -4 will then be encoded as 12, and so on and so forth for the remainder of the values shown here. And it's, I guess, important to point out here that 0 does not have a negative representation, and -8 does not have an additive inverse to get to 0. It's kind of our one extra. It's what -0 was in sign magnitude notation here. We're using that and get an extra negative value compared to the positive range. Values that we'll be able to store with 4 bits using 2's complement. And I guess the key thing to point out here is the most significant bit here. So if we look at this example, the most significant bit is not really a sign bit because it's actually contributing to the number. Because remember, like 15 now is going to be interpreted as -1 in this representation. That 1 contributing to 15 is contributing to the value encoded. It's very easy, though, when we're using this scheme to determine whether a number is positive or negative, because the n-1 bits are used for the positive side. And then you bring in this most significant bit to kind of put you over the hill, and it will allow you to, that gets you to the other side of this. And there's a 1 in the most significant bit that gets you to this side. And that side is the side storing the negative values. So hopefully that kind of makes sense. Let me jump back here to the slide deck. Oops. And we'll go ahead and finish this out. So 2's complement. The common way to represent integral numbers in memory is using binary form for positive numbers and by its 2's complement for the negative values. The question becomes, what range of values can we represent using straight binary coding and 2's complement using, say, that half byte of memory? Well, I drew it out. There's an easy formula to get it. It'd be 2 to the number of bits -1, so 2 to the 4 -1. -1 is going to be the largest positive integer that we can store using this encoding scheme. That's 7. The smallest or most negative integer value is going to be -2 to the number of bits -1. So 4 -1 is going to give us -8. So the range of values here is -8 to 7. So with that, we'll go ahead and move on to floating point numbers. I hope this makes sense. It wasn't as clear to me the first time I saw this until I realized, oh, we're splitting the range that kind of represent, or the range of values into this idea of having kind of a negative side and a positive side, and then realizing if we're equa kind of slots from when we get back over to 0 in that kind of cycle we were going through. That's when it became clear how this is working. Then also remembering that we're dealing with finite memory. So if you add 1 to 15, that gets you back to 0 because you'd be carrying a 1 and there's no place to store that 1. So again, that's the 4 kind of byte story of this. I mean, this holds true whether you're using the 4-bit story of this holds true if you're using 4 bits or 4 bytes. It's kind of the same idea. It's just the range of values increases. So see you all in the next video.